Welcome back to Quay Does Leetcode. Today I'm going to be doing problem number 297, serialize and deserialize a binary tree. So for this problem, you're given a binary tree and you need to turn the binary tree into a string. You need to represent it as a string, and then you need to take that string representation and turn it back into a tree object. So how can we do this? Well, we can do this several ways, but what I'm going to do is breadth first search. So I'm going to do breadth first search, and I'm going to represent a node value as its node, and a empty node as null or none. I'm going to use n for none. And so you go to the first level and you get the first node, so that's 1, and then you traverse the second level, so that's 2 and 3, and then the third level, 2 has no children, so its first child is going to be none, its second child is going to be none, and then 3, its first child is 4, and its second child is 5, and then 4, it's now I'm on the next level, so this is none, null, and null, and this is null and null. So it would be none, 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 none. And this is a unique string that can always be turned back into a binary tree because you're actually saying which nodes are none. So when you take this back into a binary tree, you can hold. So what you do, now you need to turn this string back into a tree. So you know that the first thing in the list is the root. So the root is 1. And you know that the next thing that comes after the root are its left child. So that's 2. And its right child is next. So that's 3. And then you know that it only has 2 children. So the next thing that must come after that is the left child of its first child. So that is null. And so that's the left child. And then the right child of its left child. And that's null. And then the next thing that must come after is its right child's left child. So that's 4. And then its right child, its right child's right child. So that's 5. So that's 4 and 5. And then you know that it can have at most 2 children. So the next thing that must come next is the children of its left. So of the right of its child, so that is null. And then the right child, null. So null and null. And then for the next level, null and null. And so that is how you build the tree. So we're doing this with breadth first search. And this will take O of n time to turn it into a string to encode, and then O of n time to decode. So let's code this up and see what it looks like in code. So the first thing that you have to do is import your deck, because you're going to be using a queue to do breadth first search. So we're going to use our deck data structure, which is a double-ended queue, but we're just going to use we're going to use it like a queue. So the first thing you need to do is take care of an edge case. So if not root, if there's no node, then you want to return just an empty string. So so now you know that there has to be a root node, and you want to make your deck. So you're going to make a queue, which is going to be your deck, and you're going to give it your root node. And you're going to loop while there is something in your queue. You're going to process the nodes, that the root node. You're going to process the node that is the next node in your queue. So your node is going to be equal to queue dot pop left, and so so then you're going to now you have your node, so you're going to check if the node has any left children. Oh, you're going to also need to have a result array for doing your traversal. So you're going to add your node.value to your result array. So result.append is you're going to append your node.val. And if you have a left child, you're going to add your left child to your queue. So queue.append node.left. And if you have a right child, you're going to append queue.append node.right. And we've already appended our node value to our result, and we are going to return, after we process all the nodes, we're going to return we're going to change our array into a string, and we're going to join it with join our result with a comma. But one thing that I forgot is that if we do not have a left child, then we actually have to say we have to append a null, because we want to, if we don't include our nulls, we don't know what our empty nodes are. So if there's no node dot left, then queue dot append a n for null, and if there's no node dot right, q, wait, actually what we're going to do in this case is we're going to instead of checking if there's a node dot left, we're just going to append the node dot left, and we're going to append the node dot right. And oops, but so it could be none, but what we're going to do is check for none here. So if not node, then res dot append none, and then we're going to continue. And then otherwise we're going to append our res.val and our left node and right node. So that's how we're going to take care of this. So let's so this should give us our encoded our string version of our tree. So let's print our result, and this should give us an array of our our breadth first search level order traversal. So let's run this and see what we're getting. So we're getting 1, 2, 3, null, null, 4, 5, null, 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 null. So that is the correct level order traversal breadth first search. So our serialize function works. So now we're going to deserialize. And for deserialize, we're going to take care of our edge case. So if not data, so data is going to be our string. If this is an empty string, then we're going to return none. So now we know that there's something in the data. So we're going to reformat it. We're going to say data equals data dot split. So this is going to give us an array that is split on the comma because we joined it on the comma there. So we're going to split on the comma. This is going to give us an array like the one that we saw in the when we ran the code. So now we have our data. So we're going to make a root node, and we're going to say our root is equal to tree node, and it's guaranteed to have at least one node in it because we already checked if not data. So we're going to have a tree node that is going to be our data at 0, and we're going to change this into an int because we were changing it into a string before. Actually, we forgot let's comment this out really quick, and let's make sure we were changing this into a string. So res equals, and then print res, return res. So we're going to run this. Oops, we need we need parentheses. So we actually need this to be a res to be a string. We're giving it node.val, so we need to change node.val from an integer into a string. So we're going to change this into a string. And now this is getting the correct thing. Where we're getting 1, 2, 3, 4, null, 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 but it's a string. So this is good. This is giving us the correct thing. So now in our deserialize, we were getting data at 0, and that was a string. So we're going to need to change it into an int. And make it our tree node. So our root is our tree node, and now we're going to make our queue. So our queue is going to be our dec data structure, and we're going to give it our root node. And now we're going to loop while there's something in our queue. We are going to so we're going to be building the tree. So our node is going to be equal to our queue dot pop left or right. So this is going to give us our root node with no children on it because we just defined our node. So what we're going to do is we're going to say, now we also need a variable for I, which will tell us where we are in our data. So we're going to start I at 1 because we already used the first position 0 for the root node. So we're going to start I at 1. So we're going to say, we're going to say if data at I is not equal to null, then we're going to say we're going to set our left child. So our left child is where data at I is. So we're going to say node.left is going to be equal to data. We're going to have a tree node, and it's going to be data at I, and it's going to be a integer of that because that's going to give us a string of the number. So we're going to make that an integer, and then we're going to actually, so now we've made this data node, we've made this left node, but we didn't actually set its children. So to set its children, we're going to need to put it in the queue. So we're going to do queue dot append, and we're going to say node dot left. And if the node is actually none, so the tree nodes, if you see in the definition of the tree node class, when you initialize it, left and right are none by default. So if it is none, then it's going to already be, if this node is n, then the node dot left is going to, if you don't set the node dot left, it's going to already be none. So you don't need to do anything. And since we added we used data I, we need to increase I by 1. Now we're going to do data, if data at I is not null again, because now data at I is we're going to increase data at I no matter what, because if it was null, we need to increase I, and if it was actually a value there, we need to increase I because we already processed it. So now we're on the right child. So we're going to do node.write is equal to tree node and int and data I and q.append that node.write, and we're going to increase our I no matter what, because if it was null, we still need to move on to the next node. And this should take care of building all of our trees, because the we're appending the children nodes, and so they'll come out up here, and we won't need to add the children for null nodes, so because they have no children, because they're null nodes. So at the end, we're just going to return the root that we made, because now this root is going to have the children, and those children are going to have children. So let's run this, and we are getting a correct answer, so let's submit. And it was accepted, and it's pretty fast. So this is a breadth first search solution. It's a O of n for serialize and O of n time for deserialize, and it's using a Q data structure. So it's O of n space as well. And that is how you do that problem. Thanks for watching, and I'll see you in the next video.